Okay, so if we take the integral of the instantaneous power, so please pay attention to the difference. Here, P is a small letter, lowercase letter. Here, P is capital letter. So P, if it is capital letter, it will be called average or real power. And the small letter, it will be the instantaneous power. So instantaneous power is the product of the time domain voltage and the time domain current. And the result of this product, we have it here. We have it here. So if you take the average or the integral for any period of this instantaneous power and divide this integral over the period. So T here is the time and T is the period. So if I go back, so T is the time in order to finish one period from this to this. So this will be T for the current, but we are talking about T for the power. We are integrating the power. So we will look for one period. So this will be the one period. So this is one period of the power. This is one period of the power. So coming, yes. So this is one period. So if we integrate this power for one period from 0 to T, so this will be T capital is time. And from this point to this point, it will be T capital. If you integrate it, so this will be the average power. And if we integrate this formula mathematically, so it will be the first component. So P, the average power, is equal to V maximum, I maximum divided by 2 cosine theta V minus theta I. So this is what you need to know. This is what you need to know. So the average power is the maximum voltage times the maximum current divided by 2 and multiplied by cosine theta V minus theta I. So again, the average power P is equal to V maximum that I can extract immediately from the time domain voltage times the I maximum from the current formula over 2 and times cosine theta V minus theta I. So this is the how to calculate the average power. So you don't need to do this. You don't need to go through this mathematics or through this. And you don't need to do the integration. You need just to apply this formula. But why we need to go why we are discussing now these formulas, because we need to understand how we came with this formula. And how we came with this formula is very simple. We made an integration over one period of the instantaneous power and divided this integral by the time of that period. So this will be the average power. And the average power, it is called the real power because it is the power that can be converted to useful form of energy, which it could be mechanical energy or light or heat. So this is how we use electrical energy. Electrical energy is used as a mechanical energy, for example, in the washing machine, or used light in lamps and TV and whatever else, or used as a heat in the heater, in the kettle, in the iron. So these are the three forms, useful forms of energy to which electrical energy is converted. So only these three forms, either mechanical energy in motors, either lights in lamps, TVs, phones, etc., either heat in iron kettles, etc. So this is why it is called real. It could be called as useful energy and average, real, or useful energy. So these are the names of the average power or real power. Or it could be called also active power, active power. So active power or average power or real power or useful power all are the names of the power. In real life, we call it, in practical life, we call it active power, active power. And on the other hand, we have reactive power. And the reactive power is denoted as a Q. And if we look at the reactive power, it is also V maximum times I maximum over 2, the same as here, but multiplied by the sine, the difference of the angles, not by the cosine. So the only difference between the active and the reactive power in terms of calculation is we have sine function here while we have cosine function. The same phase angle of the voltage minus the phase angle of the current. So this is the active power, this is the reactive power. The reactive power cannot be changed, converted to mechanical or light or heat. So the reactive power is that power that is stored in the inductor, or in the capacitor. So we talked about stored energy in the inductor. It will be half Li squared. In the capacitor, it will be half C V squared. So this energy is a reactive in power, and this this energy is the stored energy in the inductor, and this energy is the stored energy in the capacitor. The stored energy in the inductor and the stored energy in the capacitor can be calculated knowing the reactive power. The reactive power. So the reactive power is stored in magnetic fields or stored as electric fields. Electric fields in the capacitor, magnetic fields in the inductor, and they are not they cannot be converted to either mechanical or light or heat. So this is why they are called reactive. So while active or real or useful can be converted to three types, which are mechanical, energy, light, or heat. Any questions, please, on this slide? Is it understood, please?
Yeah, I get it. Thank you.
What about other students? Any other responses? Is it understood? Okay. So these formulas that you need to deal with. P is equal V maximum I maximum over 2 cosine the difference in the angle, and the Q, the reactive power, is V maximum I maximum over 2 sine the phase shift between the voltage and the current. Okay, now let's have a look at average power in the different components. So the first component is a resistor, and then on the next slides we will see the inductor and the capacitor. So in the resistor, we know that the voltage and the current are in phase, and if they are in phase, they should have the same phase angle. So theta V and theta I are equal to each other, so they are in phase. Okay. So, and this is the formula of the instantaneous power extracted from the previous slide. So we have three components. One component, the first component, is the average power P, or the active power P. The second component is also P multiplied by cosine 2 omega t. So P multiplied by cosine 2 omega t. And here, if theta V equal to theta I, so the difference will be 0, and sine 0 is equal to 0. So this component will be equal to 0. This component is equal to 0. So what we have here, we have one constant value, and we have a sinusoid with a double frequency, and the magnitude of the sinusoid is the same as this constant value. So here is the constant value, here is P capital, and we have the magnitude of the sinusoidal component will be twice, will be 2, because this P is given as 1. So it will be twice. So this is, as you see here, we have this sinusoid, the maximum of which P, which is 1, and you are shifting it up by the same value. So the magnitude here will be 2. And since here at the 0 time, cosine of 0 is equal to 1. So at 0 time, we will have the maximum value. So the maximum value here is 2. And as you see that the sinusoid, double frequency sinusoid, is completely above the x-axis, is completely above the x-axis. It is shifted above the x-axis, and it's, let's say, negative peak. What should be negative peak is at the 0 axis in this case. So if you take the average value for any given period, here is one period. If you take the average value of this period, it will be this P. This is why this P is given in capital letter, while this P is given in a small letter. So this sinusoid is the instantaneous power, this one, and this line, straight line, is the active power P, is the active power P. So for any purely resistive circuit, the average power or active power will be V maximum, I maximum, divided by 2 cosine theta V minus theta I. We know that theta V and theta I are equal because this is a resistive circuit, and it will be 0. Cosine 0 is 1, and this will be V maximum, I maximum over 2. So this is how to calculate the active power in a resistor. So it will be V maximum, I maximum over 2. This is in case of a resistive circuit, in case where theta V, the phase angle of the voltage, and the phase angle of the current are equal to each other. Any questions, please, on this slide? Okay. Now we have purely inductive circuit, a purely inductive circuit. And in a purely inductive circuit, we know that the current in the inductor, IL, lags the voltage across the inductor, VL, by 90 degrees, by 90 degrees. So if the voltage of the phase angle of the current will be the phase angle of the voltage minus 90 degrees. So the peak of the current will occur after 90 degrees of the peak of the voltage. So this is why we have a lag current. So and this lag or phase shift is 90 degrees. So again, this is the formula in general that we had in a previous slide, that we derived in previous slide. And now I see that if I make it as theta from here, theta V minus theta I will be equal to plus 90 degrees. So now I can replace here 90 degrees, cosine 90 is 0. So this first component is equal to 0. And here I can have 90 degrees, cosine 90 degrees is 0. So the second component is equal to 0. And you can have here 90 degrees. So sine 90 degrees is 1. Then it will be Q, which is V maximum, I maximum, over 2 times this sine angle times the sine omega 2. So this is the average, sorry, the instantaneous power. So this is the instantaneous power. And if we draw this instantaneous power here, so we will see that this instantaneous power has also a sinusoid with double frequency. We have the x-axis, please pay attention here, that here we have the x-axis. So we see that this double frequency sinusoid is symmetrical with respect to the x-axis. Its positive peak is 1 unit. Its negative peak is negative 1 unit. So if you take the average over one period, it will be equal to 0. So P, the average power, is equal to 0. And we saw here that this component is equal to 0 since cosine 90 is 0. So the average power is 0. So there is no average power in the inductor. There is instantaneous power, which is given as a double frequency sinusoid, but its average is equal to 0 because, as you see, it is symmetrical to the x-axis. So what is the Q? What is the reactive power? So engineers agreed to call the peak of this sinusoid to be Q. So Q, the reactive power, is the peak of the instantaneous power sinusoid. So again, I will repeat it again. So Q, which is the reactive power, is the peak of the instantaneous power, in this purely inductive circuit. So as you see here, we have this line will represent Q, which is the reactive power. In order to distinguish between these types of power, the average power P is measured in watt, and the reactive power Q is measured in volt ampere because it is the product of the voltage and the current. And we add the letter R, to indicate that this is a reactive power. So it could be written all capital letters, or it could be written as small letters. So here we see that all the unit V volt ampere R, volt ampere reactive, and we say VAR. It could be capital letter VAR or a small letter VAR. So as you see that, again, the first component is equal to 0, the second component is equal to 0, and the third component is given as a double frequency sinusoid, double frequency sinusoid. Any questions, please? Is it clear, please? Okay, so
Yes, thank you.
So here we need to memorize this, that the average power in a pure inductive circuit is equal to 0. So you can memorize it or you can calculate it, but and you will have it as 0 at the end of the day. And the last component here, passive component, is the capacitor. And we know that in the capacitor, I through the capacitor leads the voltage across the capacitor by 90 degrees. So we say that theta I, the phase angle of the current, is equal to theta V, the phase angle of the voltage, plus 90 degrees. And from here, I can say that theta V minus theta I will be equal to negative 90 degrees. Again here, if you plug negative 90, so this component will be equal to 0, this component will be equal to 0, and this component will be here. So here we have the instantaneous power, and it is given as negative Q sine 2 omega t, where Q is this component, Okay, and again, if we draw this sinusoid on the this graph, we will see again, this is the x-axis. We see that this sinusoid with a double frequency is symmetrical with respect to the x-axis. So its average over any period, for example, this period, will be equal to 0, because if you add up all the positive values and the negative values, so their sum will be equal to 0 divided by the number of these values, it will be 0. So the average here, average power, which will be equal to 0 as well. While the reactive power, which is the magnitude of the double frequency sinusoid, here it will be the reactive power and measured in volt ampere reactive. In order to distinguish between the reactive power in the capacitor and the reactive power in the inductor. So the reactive power in the capacitor is given with a negative sign, So Q here in the capacitor, QC is a -1 var, while in the previous slide, QL was given as 1 var. So positive capacitor Q indicates that you have inductive circuit. Negative Q indicates that you have capacitive circuit, And again, for both the capacitive and inductive circuits, pure capacitive and pure inductive circuits, the average power is equal to 0. While if I go back to the resistive circuit, I see that here I don't have the third terminal, which is Q. So Q in the resistive circuit is equal to 0. So in the pure resistive circuit, the reactive power is equal to 0. So if I will summarize before I go further, so I will say that let me clear this part of the slide. Okay, so let me summarize. So we have, if you have a pure resistive circuit, then P will be equal to V maximum, I maximum over 2 cosine theta V minus theta I, which are equal, and Q will be equal to 0. If you have a pure inductive circuit, L, then P is equal to 0, and Q will be equal to V maximum, I maximum over 2 sine theta V minus theta I, which will be sine 90 degrees, and sine 90 degrees is 1. So it will be V maximum over V maximum, I maximum over 2. And if you have a capacitive circuit, again, the average power is equal to 0, while Q will be equal to V maximum, I maximum over 2 sine theta V minus theta I. And the difference theta V minus theta I is equal to -90, and sine -90 is -1. So it will be negative V maximum, I maximum over 2. So this is what you need to know from the previous 3 slides. So the previous 3 slides with derivation, with the proof why they are like this, but this is actually what you need to know as an electrical engineer. So this is the summary. And here we have the power factor, So the difference between the phase angle of the voltage and the phase angle of the current is called the power factor angle, And the power factor can be defined as cosine of this angle, And we see that cosine of this angle is there in the average power formula, is there in the real power or average power formula, cosine V theta V minus theta I. So this portion is called the power factor. This is also called the reactive factor. So this is the power factor. This is called a reactive factor, But in practical life, we don't use it, but you can find it in textbooks and in some papers as a reactive factor, because it is associated with the reactive power, but we don't use it in practical life. What we use in practical life is the power factor, which is the cosine of the angle difference between the phase angle of the voltage minus the phase angle of the current. So this is called power factor. So this is power factor angle, and this is the power factor. So we have 3 types of power factor. We have power factor in resistive circuit, and we have power factor in inductive circuit, we have power factor in capacitive circuit. So lagging power factor implies that the current lags the voltage, and the current lags the voltage if you have an inductive load. So it is not necessarily to have a purely inductive load, because in real life we cannot have a purely inductive load, but in most cases it will be a resistive inductive load. So if you have a resistor and inductor in a circuit, RL circuit, it is still called an inductive load, And most loads in our real life are inductive loads. So most loads are inductive loads, and so most power factors that you will deal with in our real life are lagging power factor, So this is the most common case, Why is that? Because we are converting electrical energy mostly to mechanical energy and in the motors, and the motors are resistive inductive load. So if you have a capacitive load, which could be a pure C in theory, or RC in practical life, so this power factor will be leading power factor, because the current in this capacitive circuit will lead the voltage, because the current will lead the voltage. So we call it leading power factor. And as you know, since the power factor is a cosine function, so it will be changing from 0. So the power factor will be changing from 0 up to 1, So it could be a 0 if you have a pure inductive or a pure capacitive circuit, and it could be 1 if you have a pure resistive circuit, R. And we can have R in theory, and we can have it also in practical life. And then the power factor will be called the unity power factor, because in a resistor, the voltage and the current are in phase, and the phase angle between the voltage angle and the current angle will be 0. And then cosine theta V minus theta I will be equal to 1. And this is why we call it a unity power factor. So unity power factor is the power factor that is equal to 1. And this can be achieved in a resistive load, or it can be achieved also in the RLC circuits, in which L and C cancels each other, because the inductor and the capacitor behavior in the RLC circuits are opposite to each other in terms of lagging and leading. So if they will cancel their effects, so the circuit, although the circuit will be RLC circuit, but it will behave as a pure R circuit. So this is called the resonant circuits. And I believe resonant circuits will be there in communication courses. So resonant circuits are circuits in which L and C cancels each effects, and the circuit will behave as it is only a resistive circuit. So these are the 3 types of the power factor that you may encounter in this course or this subject. Any questions, please, on this? Any questions on this slide? Is it clear, please?
Yeah, it is. Thank you. For me.
Okay, let's go through an example, so we to make sure that we understand what we had here. So example, so we have here a circuit. Sorry. So here we have a circuit, and we have a time domain voltage and the time domain current. So I need to find the average power and the reactive power, So before I start, I need to make sure that the time domain voltage and time domain current are given in my standard form. So I see the maximum voltage, the maximum current, it's fine. I see cosine function, but here what we have sine function. So the first thing that I need to do is to convert this sine function into a cosine function. So the current then will be given as negative minus 15 minus 90 degrees. So it will be minus 105. So you need to deduct 90 degrees from this angle in order to convert sine function to cosine function. So now this is the voltage that I will deal with, and this is the current I will deal with. If you are using this angle, everything will be wrong. So what I need to calculate? I need to calculate the average power. Here is the formula. V maximum is 100 from this expression. I maximum is 4 from this expression, sorry, over 2 cosine theta V 15 theta I negative 105. If you apply this, then you will have negative 100 watts, negative 100 watts. We will discuss the negative sign a few seconds later. And I need to calculate the reactive power, and here is the formula. You need to multiply the maximum voltage with the maximum current over 2 and sign the difference in the phase angles. So maximum current is 100, maximum voltage is 100, maximum current is 4 multiplied by half, and sign the phase angle of the voltage is 15, the phase angle in the current is negative 105, and this will be this much. 173.21 watt, 2.1. Okay, so positive values mean consumed. Positive values means consumed, while negative values, these are positive values, while negative values means delivered. Means delivered. Okay, so the negative value, negative 100 watt, means that the network inside the box is delivering. So this box is giving me 100 watt. And the Q is positive. This means that the network inside the box is absorbing or is consuming the 173 watts. So this is also you need to pay attention to. This is because of the passive sign convention. So you can have passive sign convention or generator sign convention or active sign convention. But in our course, we will deal only with the passive sign convention, which means any positive values in P or Q means that the network consumes or absorbs this amount of P and this amount of Q. Any negative values in P or in Q will mean that the network delivers or gives us this amount of P or Q. Any questions, please, about this example? Okay. So here we have a similar, typical table for the equipment in any house. So what we have here, we have, as you see, that the equipments are given in their average power. So average power is used to be the rated or the ratings or the given value of the equipment in your house and in industry as well. So coffee maker is 1200 watts. So these are in watts, okay? Dishwasher, 1201 watt. Egg cooker, 516 watt. Laundry, clothes dryer, around 5000 watt. Air conditioner around 1000 watt, fan 88 watt, and so on. So as you see, you can have all the equipment here, and these are the typical values of their powers, So plus minus, so you can make a list in your house and see how much is the power in your house. And in order to calculate the energy, the energy is equal, to the power multiplied by the time. multiplied the time. So the power usually is given in kilowatts and the time is in hour. And the result will be the energy in kilowatt hour. So this is what you pay for, to the company, to the electrical company. So 1 kilowatt hour, I think in our region here is called for 19 cents. So 19 cents is the cost of 1 kilowatt hour in our region. So it could be plus minus, doesn't matter. So what you need to do is to calculate, to multiply the power of the coffee maker, for example, by the time that you are using every day and every month and every year, because this is annual consumption, So it will be 140 kilowatt hours, 140 kilowatt hours. So you need to pay 140 times these 20 cents or 19 cents every year to use this coffee maker. If I calculated, so I can use the formula to find the time. I can use this formula to find the time. So I have the energy, which is 140. I have the power, which is 1200. So if I divide the energy, which is 140 kilowatt, if I divide it by the power in kilowatts, which is 1.2. So this is, if you convert it to kilowatt, it will be 1.2. So this gives me that I'm using the coffee maker 116 hours a year. If I divide it by 12 or by 365, I will find that I'm using 8 for 19 minutes every day. So this data for this coffee maker is given if you are using the coffee maker for 19 minutes every day. How I can calculate the time? So the time will be equal to the energy in kilowatt hour over the power in kilowatts. Then the time will be given in hours. Then this time you divide in hours, you divide it by 365, which is the number of days in the year. Then it will give you the time per day, per each day. So of course you can list all the equipment in your house, and you can see the power is written there on each equipment. You will see that it is given the power, okay? And you can estimate how long you will use this equipment every day, and you multiply the time, daily time, by 365, and then by the power. It will give you how much kilowatt hour you will pay annually. So this is very nice table. Please give it some time, try to understand it. And if you have any questions, I will be more than happy to discuss them. So here we have one example. Let me see how many slides I have left here. Okay. So let's go through this example. For example, here we have the voltage and the current, and we need to calculate the power and the average power and the reactive power. So again, in order to calculate the active power, you need to use V maximum, I maximum over 2 cosine theta V minus theta I. In order to calculate the reactive power, it will be V maximum, I maximum over 2 sine theta V minus theta I. So let's double check. So what we have here, we have V maximum. We need to make sure that both of them are given in cosine function. And I see that all variables are given in standard form. So what you need to do is multiply y 100 by 20. So 100 by 20 over 2, it will be 2000. It will be 2000. And then cosine negative 45 negative 15, so it will be negative 60 here, and cosine 60 is negative 60 is half, and 2000 times half, sorry, 1000 times half, it will be 500. So as you see, it is 500. And in order to calculate Q, you need to multiply the maximum value of the voltage, 100, times the maximum value of the current, 20, over 2. So the top is 2000, over 2 will be 1000. And sine negative 45 minus negative 15, it will be negative 60. And the sign of negative 60 is negative 0.866 multiplied by 1000. It will be a negative 866 point something. Okay, so as you see here, it is negative 866 watt. So this means, as you see, the direction is the current is going to be. So this is 500. So 500, since it is positive, so it goes from A to B. So B is consuming, is absorbing 500, and 500 is coming from A. While the bar is negative, so the bar is going from B to A. So B is delivering the bars while A is consuming the bar. So the bars are going from B to A, and so on. Similarly, you can do all of them. Any questions on this example, please? So this is what we learned, and this is what we need to memorize. So this is very simple, two formulas that you need to keep in mind. Okay, the last thing to discuss today is the RMS and power calculations, the RMS value. So the RMS value is root mean square. So root mean square. So this is the RMS value. Why we are using this RMS value? So if you have the voltage or the current given as a sinusoid, and you need to express a constant value for this current or voltage. So you see that the voltage or the current is changing all the time. So if I ask you what is the current now, you will say 0. After a while, you will say 1. After a while, you may say 5. After a while, you say 3. After a while, you say negative 1, and so on. So we need to have one constant value to express the current. If we take the average, the normal average, since the sine wave is symmetrical with respect to the x-axis, it will be 0. So the normal average is equal to 0. So what we need to take is the root mean square. And the root mean square is the average of the squared value. So if you square this value, so it will be something like this and like this. So if we take the average of this squared value, then it will be a constant number, and this constant number will be good to represent the current, will be good to represent the current or any sinusoidal value. So the average value, the root mean square is the integration of, here we have a voltage given as, let me write it here, V of t is given as V maximum cosine omega t plus theta v. So this is the standard form. Now I want to square it. I want to multiply it by itself. So this will be V maximum square cosine square omega t plus theta v. Theta or phi, it's fine. So it could be theta or phi. So it's just a symbol. And I need so this is the average, and I want to integrate it over one period and divide it by this period. So this will be the RMS value of the voltage. So this will be the RMS value of the voltage. And if I divide the RMS value of the voltage by the resistor, according to Ohm's law, it will be the RMS value of the current. So I RMS is equal to V RMS divided by the resistor. So if I divide it by the resistor, so it will be, okay, sorry, we are calculating the average power here. Sorry, I'm sorry for that. So let me start over. So in order to calculate the power, we know that the power in a resistive circuit can be calculated as V square over R or as I square times R. So we had these two formulas in previous discussion. So now I want to calculate the power. So the power is the average power is the integration of the instantaneous power. So the instantaneous power is the product of the instantaneous voltage times the instantaneous current, and the instantaneous current here is I of t equal to V maximum cosine omega t plus theta v over R. So this is the current. The current will be the current, instantaneous current will be the instantaneous voltage according to Ohm's law divided by the resistor R. Now I want to multiply V of t by I of t. So this will be the instantaneous power. And if I integrate this instantaneous power over one period and divide it by the period time, it will be the average power. So I'm calculating here the average power. So let's multiply these two expressions with each other. So V maximum it will be V maximum square, cosine times cosine, it will be cosine square, and here over R. And I'm integrating this expression, which is this expression is P of t. This expression is P small or P of t, the instantaneous power. I'm integrating it over one period and dividing it by that period, so it will be the average or real power. So the average or real power. Since R constant, I can take it out of the integral sign. So here is R. So and now what I have here is the average of the squared of value of the voltage. So here, as you see inside the integral sign, is V maximum square cosine square omega t plus theta V dt, which is the square of this expression. So I'm squaring this expression, taking the integral over one period and dividing of that period. This is called RMS value. So this is the RMS value. You square the function and then you integrate it over one period. You integrated over one period and divided by that period to take its average. So this is RMS. So as you see that this power is equal to the RMS value of the voltage square divided by R. So here V RMS square divided by R. So this is the average power, and this is using Ohm's law. We can replace V RMS square by the current, and then the power can be equal to I square RMS times R. So let me show it here. So P is equal to V RMS times I RMS, and I know that V RMS is equal to I RMS times R, or I RMS is equal to V RMS over R. So if you replace V by I RMS over R, then P will be equal I RMS square times R. And or if I replace this I RMS by V RMS over R, then P will be V RMS square over R. So we can use this formula, or we can use this formula. And this is how we came to these formulas. Of course, you don't need to memorize this derivation. You need to memorize these two formulas, but this is in order to understand how we came to this formula, And these are the two formulas that we had in the previous class, the previous slide. And this RMS, so we see that V maximum, I maximum over 2. And we know that the RMS value, so V RMS is equal to V maximum over square root of 2. This is only for sinusoids. And I RMS is equal to I maximum over square root of 2. So if I replace this 2 by square root of 2 times square root of 2, So V maximum over square root of 2 can be replaced by V RMS, and the I maximum over square root of 2 can be replaced by I RMS. RMS and the effective values are the same. So RMS or effective. So here it's written effective, right? Or you can write it effective, it's the same. So as you see that V can be calculated as V effective, I effective cosine theta minus theta V minus theta I. So if you are using maximum values, you need to divide by 2. If you are using effective or RMS values, you don't need to divide by 2. For a Q is the same. A Q was calculated as V maximum, I maximum over 2 sine the phase shift. And here we eliminate this 2 and using the RMS or effective values. So V effective, I effective sine theta minus theta V minus theta I. So what is the, let's say, physical meaning of the effective value? So here we have a DC circuit, here we have AC circuit. So if you have a lamp here, so this lamp will give you a certain amount of light. If you want to have the same certain amount of light by replacing the DC source by an AC source, so you need to have an AC source that has the same value of the DC source, but this value of the AC source is the RMS value. So the maximum value here will be 100 times square root of 2, while the RMS value is 100. So this is why it is called effective value or RMS value, because it will be the same as if you are using the DC circuit. But in AC circuit, it will be 100 RMS value, which means that the peak of this sinusoid will be larger by by square root of 2, and this is why Thomas Edison was not encouraging the use of this circuit. Okay, here we have an example that we will discuss next class. I don't want to take more time from your time. So if you don't have any questions, let's stop at this point, and next class we can continue this example. Any questions, please? Any questions? Okay,
No,
if you
not for
don't
me.
have any questions, so see you next week.
Thank you very much.